Hello everyone, can you hear me? Uh, if you can, please let me know in the live chat that you can hear me. So, can you all hear me? Awesome. Awesome. Thanks, Akshay. Yep. So, again, good morning everyone. I'm Sai Avinash, and in this class, I'll be teaching the other variation of Knapsack, the lesser known variation of Knapsack. So, yeah, I'll be teaching that. So, I'm Sai Avinash, and I'm an SRE at Google Dublin, currently working there right now. I'm all India rank 4 at Code Chef. My maximum is International Master at Code Forces. I SD intern at Uber, and I'm also a Snackdown finalist. The subjects that I take are discrete maths, dynamic programming and graphs, and a lot of other competitive programming topics. Use the code SciLive to get a 10% off on the Unacademy Pro subscription. All right? Yeah. Also, if you find these like topics a bit, if you find Knapsack a bit harder to understand, you can look at the first few videos to get a grasp of dynamic programming, and then come to this topic. Or like you don't really need much prerequisites to come to this topic, but if you find this really hard, you can move to the first few videos. Otherwise, you can feel free to watch this video and judge for yourself. So what do we have here? So we have college projects. It's a show every Friday night at 10 p.m. by Raj Vikramaditya, Striver. So this is a part of Unacademy's career as a software developer subscription at only $9.99 per year. V Chandu 7-star. So it's a show every Friday night at 10 p.m. and he's going to cover what you need to improve in a resume, like in your college projects, and what can be done to improve and what's missing there and so on. And that will help you build your career in general. And there's this course called the CodeChef Apprentice. It goes live every Saturday afternoon at 2 p.m. This is a course where I pick a beginner who wants to become a mentor. This course is taken by me, who needs a mentor. Just for 1 hour, I'd be mentoring him or her, and then I'll be clarifying their doubts. They'd come to me with problems, and then I'd explain it to them right in front of everyone. So they'd be asking me doubts, and you can ask me doubts as well if you're there. So if you're an absolute beginner, or if you just started competitive programming, you can ask your doubts too in the chat. I'll be active there. So feel free to come there and make sure that you get your doubts together so that I can answer them, blockers or anything. I'd be really happy to answer them. So, and don't forget to use the code SciLive before you're subscribing. That's that. It's taken by me. So do subscribe to this channel. Do subscribe to this Telegram channel. There are going to be live updates about the latest videos and so on, so that you don't miss anything. And if you think the last video is useful and this video is going to be useful to you, if you think it's going to be useful, do like and share it with your friends. Knowledge is best when shared. So yeah. And if you haven't subscribed already, what are you waiting for? So we have Knapsack 2. It's the absolutely same problem. Okay, wait. Aniket's asking how did I get there? I mean, I guess I was doing competitive programming regularly and they contacted me. You can usually apply through referrals from what I understand. If you know someone from there, you can apply through referrals. That's how it works, usually. All right, let's look at the problem now. Knapsack 2. So what do we have here? We have n items. This is the same as Knapsack 1. We have n items numbered 1 to n. There are n items numbered 1 to n. For each item I has a weight of wi and a value of vi. Taro has decided to choose some of the n items and carry them home in a knapsack. The capacity of the knapsack is w, which means that the sum of the weights of items taken must be at most W. Again, it's absolutely the same as the last problem, with one condition. With one condition. With one condition. What's the condition? What do we have here? What do we have here? We have n is up to 100. The weights are up to 10 power 9. And the value is 10 power 3. The weight is 10 power 9. So we cannot do the same approach that we did last time here. We cannot do the same approach that we did last time here. Right? Last time, what did we do? We did an O of n into W approach. It passed because W is up to 10 power 5. Now, W is 10 power 9. And now it won't work anymore. 100 into 10 power 9 is 10 power 11. And in 1 second, you can do only about 10 power 8 to 10 power 9 operations. So this is not feasible. Yes, the weight is 10 power 9. This is not feasible. How do you do this now? How do you do this? How do you do this? But one more observation is the values are up to 10 power 3. So can we do something about that? Can we do something about that? The values are up to 10 power 3. Can we do something about that? Awesome. Can you do something about that? Turns out we can. First note that the people who have come here for the first time, the problem is basically you have n items and each item has a weight and a value. Each item has a weight and a value. First item, second item, and so on. The examples are also absolutely same as the last problem. If you haven't watched the last problem, I'd suggest you to watch it too, but you don't need to watch it yet, right? All right, now in this problem, you have n items. Each one has a weight, each one has a W. Each one has a weight and each one has a value. And you have a budget again. Now you need to pick a bunch of items so that you don't exceed the budget. While not exceeding the budget, what is the maximum value you can get out of those items? All right, you might not be able to pick all of them because it can exceed your budget. Got it? Any doubts in the question? 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 Yes. Yes, Raj, it's gonna go about 1 second. Akshay, you deleted something. I don't know. No doubts. Okay. Awesome. 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 All right. Then, how do we do this? In the last problem, again, here the constraints are our hints. Constraints are our hints. All right. What are the constraints here? Weight is n can be up to 100. Sorry. Weight can be up to 10 power 9, meaning O of n W won't work. Got it? All right. Now values are up to 10 power 3. Values are up to 10 power 3. Now Vi is up to 10 power 3. Meaning our total value can go up to 10 power 5. When, for example, if we take 100 values, the total values can go up to 10 power 5. So, okay, let's keep that aside for now. Total values, because 10 power 3 into 10 square into 100 is 10 power 5. All right, let's keep that aside for now. Now, previously, what did we define our state as? What is the best value for n items and if our budget is W? If you have n items and our budget is W, what's the best value? All right. But we can't do this anymore because clearly it exceeds the time limit and the memory limit. What do we do now? We do the reverse. What is the lowest weight? Lowest weight if we have n items and we want to achieve value, lowest weight, n items and we want to achieve value, what is your, if you want to achieve value, what is the lowest weight that you can, lowest weight with which you can achieve value? Got it? The lowest weight with which you can achieve value. And once we know the lowest weight with which you can achieve value, let's compute this array. And we find the maximum value for which the lowest weight is less than or equal to w. So let's say we know the answer for this for all n comma value. We find maximum value for which lowest weight. I'll tell you how to compute this later, but let's look at how the solution is going to look like. We find the maximum value for which lowest of n value is less than or equal to w. Find the largest value for which we know that as the value goes up, the cost, like the weight of the items, also goes up. So we find the maximum value for which the total weight is the lowest possible weight that you can get the value. It's less than the budget. Okay. Akshay, which part do you want me to explain again? Of course, I'm going to explain in a second. Chances are you won't get it in the first go. All right. Lowest weight of n comma value is basically, you have n items. Now, what is the best possible weight that you can achieve? Like the lowest possible weight needed to get value. All right, we'll take it with an example. No worries, we'll take it with an example. For example, we have 38, 330. We have this. Let's take this example itself. Let's take this example. So we have weights here, values here. Weights 3, 4, 5, 30, 50, 60. Now, lowest weight of, let's say we want to compute 3, 90. Or let's say lowest weight of, you want to compute 3, 120, 140. All right. Lowest weight of 3, 140. Note that it can be possible that you cannot reach some values. For example, you won't be able to reach the value 101 because all the numbers are multiples of 10. All the values are multiples of 10. And there's no way you can sum them up and reach 101. So we'll keep that aside for now. We'll call the weight as infinite for them. But wait, we'll get to that later. So lowest weight of 3, 140 is basically the lowest weight that you can achieve with 3, 140. Okay, just give me a minute. We'll add another value here. I'll tell you what the value is. One sec. 2. Weight is 2 and value is 40. All right. Weight is 2 and value is 40. Awesome. Now let's calculate lowest weight of 90 instead. 3, 90. 3, 90. So now we have 4 elements. So let's calculate lowest weight of 4, 90. 4, 90. So we have 4 elements. We need to pick some bunch of them so that the value is 90. Now we want to find what is the lowest weight we can achieve it with. Okay. One way to achieve it is to pick 5 and 3, the first element and the third element. So basically, we pick this element 3, 30 and 5, 60. That way you can get 90. The other way is also 2 and 4. We can pick this as well. Right. 2, 40 and 4, 50. There are multiple ways to get the value 90. But what is the way that we can get in the choosing such that the weight is as low as possible? So this is one way and this is one way. What is the weight of this? 3 plus 5, 8. 2 plus 4, 6. So the answer, lowest weight of 4, 90 is 6. I'll tell you why this is useful later. First, let's get this concept clear. So we have 4 items and we want to achieve the value 90. What is the lowest weight we can achieve it with? Which arrangement will give us the lowest weight? If there are no arrangements, then we'll call the weight as infinite so that we can get our calculations easier. Okay? Is this clear so far? Is this part clear? Is the definition of lowest weight clear first of all? Is the definition of lowest weight clear? Any doubts? Awesome. Okay. Okay. Now we know what lowest weight is. Okay. We know what lowest weight is. Basically, lowest weight, let's call that as LW of n comma v. We know that we have n items and we want to reach the value v. There are multiple ways to reach it. What is the best way? Like which way will give us the lowest weight? We are doing the reverse operation. Instead of fixing the weight and increasing our value, we are fixing the value and decreasing the weight. That's what you're doing here. Okay. All right. Now what will be our answer? Like we'll have a lot of numbers here. Like we'll have, let's say we know this value for all n and all w. We know this value for all n and all w. All n and all v, sorry. We know this for all, and say we have our budget as w. Now what we do is, we look at all these values and we just pick all the n comma w, n comma v, where lowest rate of n comma v is less than or equal to w. And out of all such n comma v's, we pick the one with the maximum value. So what we get here is, we get the maximum value whose weight is less than or equal to w. And we print that value, simple, that's it. So once we've computed this, we can find our answer. Max v, v best. Max v best, where the lowest weight of n comma v best is less than or equal to w. This is clear. Is this part clear? And we just print we print v best. That's it. This is our answer. Is this part clear? We're being greedy about constructing the DP basically. So the DP of n comma v is basically the lowest weight you can achieve with having a value v, but sometimes you might not be able to reach the value v no matter how you pick your items. But that's okay. We'll assign the value, the weight as infinite, meaning we'll never use the state. Yuvraj, which part? I'll explain it with an example, no worries. I'll explain it with an example. I'll explain this one with an example. After the lowest weight, when we have got the lowest weight, okay. What do you mean? So, okay, let me give you an example here. Let's say the weights are 2, 3, 4, 5. Values are 6. Yes. Let's call this 6 instead. 6, 5. What's it? 6. All right. This is about 2, maybe, I guess, 20, 30, 40, 50. All right, awesome. Now we'll get multiple. We'll have multiple. What do you say? And let's call the budget as say. Wait, let's call this. Let's call the weights as 20, 30, 40, and 60 as well. Weights are 20, 30, 40, 60. Values are 20, 30, 40, 50 instead. Okay. All right. Let's call the budget as 75. Budget is 75. Budget is 75. Now, LW, we'll have a lot of LWs here. Lowest weight that you can get with, for example, we can say 4, comma, if you want value of say 90. Budget. Value 4, comma 90. What is the best you can get with 4 and 90? Like best 90. You can get 40 and 50, or you can get 100. Like if you choose these two, our total weight would be 100. If you choose these three, total weight would be 90. So the best value would be choosing these three. Like if you think about it, lowest weight with 4 and 90 is basically 20 plus 30 plus 40, 90 again. Now, but this is above our budget. Lowest weight of 4, comma, let's say we take maybe 80. We can either pick, I guess, 40 and we can't pick 40. We can pick 30 and 50. We can pick these two. 30 plus 50 is 80. There's no other way to get 80, right? If you look at it. So the lowest weight is 30 plus 60. There's only one way. Again, 90. Let's take lowest weight of say some other number, say 40, comma 70. So we can pick these two. We can pick these two, right? To get 70. Or we can pick these two as well. We can pick the first and last, or we can pick the second and third. If we pick the first and last, total weight would be 20 plus 60, which is 80. Min of 80, comma, what else is that? 30 plus 40, 70. This is basically 70. Awesome. So basically 70 is our answer, because we can't reach anything between 70 and 80, right? Like I can write that down, but you can't reach anything. The answers are going to be like infinite, because we can't, it's unreachable. But lowest weight of 4, comma 70 is 70. Right? Because we can choose these two elements. And 70 is under our budget. That means the value is 70. Note that this 70 is the value. This 70 is the weight. Best weight. We can achieve the value 70 with weight 70, which is under our budget. So we win. 70 is our answer. Because everything above that, I can write 71, 72, 73 and so on. But it's not worth, because like you can't reach them. All of them are multiples of 10. So we can't reach 71, 70 and so on. I just wrote 70, 80 and so on. That's it. All right. Awesome. Is this clear now? So 70 is our answer here. With budget 75. 70 is the highest number you can reach, highest value you can reach while keeping the total weight under our budget. This is above our budget. This is above our budget. But when we decrease our value a bit, our weight is decreased to being under our budget. So this is our answer. Is this clear? Is this clear so far? Awesome. Akshay, is this clear? Thanks, Yuvraj. Other people in the live chat as well. Is this clear? If it's clear, do let me know it's clear. And I'll move on to how we're going to compute the lowest weight as well. It's a different concept, but it's a similar concept as last problem, but I'll just cover it as well. Yep. Is this clear so far? Great. Awesome. Now, let's get to the solution now. how on earth are we going to compute this? It seems a bit complicated, but no problem. Let's do it. This is a bit complicated, but we do it. So LW, we discussed what LW is, lowest weight that I can get with n items and value v. Again, there are two things you can do at nth items. You either pick the nth item, or you don't pick. We just call leave nth item, leave out. What do we reach here? And we take minimum of both cases, because we want the lowest value, right? Lowest value. We pick the nth item and see if we get the lower value, and we leave out nth item. If you pick the nth item, then our weight would be Wn plus Wn plus, now that we're picking the nth item, lowest weight n minus 1 items are left, and lowest weight n minus 1. And what is our new value? Can anyone tell me what the new value is in the live chat? V minus Vn, comma, if we don't pick the nth item, it's as good as having n minus 1 items, and same n minus 1, comma. This is if we pick the nth item. This if we don't pick. This if we pick, this if we don't pick. This is clear. If we pick the nth item, we add nth weight. Now we have a smaller problem. This is essentially LW of n minus 1, comma, weight minus, since we picked the nth item, our value, we need to now achieve a lower value, which is V minus Vn. And we are adding weight to this, lowest weight of n minus 1 and value as V minus Vn, and then we are adding Wn to it. Got it? Is this clear so far? Any doubts with this? Any doubts with this? I need you to understand this. Is this clear? Do you want me to re-explain any part? This is a recursive approach to this. Awesome. Awesome. So Yuvraj asks, when you're selecting n, why are we doing n minus 1 in the other part? So because n represents, we are doing n minus 1 because like we are not choosing the nth element anymore. So it's as good as having n minus 1 elements now. Now that we decided not to choose it, we ignore it. Now we have n minus 1 elements. Akshay is asking, if for every question, do we need to make this choice diagram and solve? It makes your life very easier if you do it. Some people do it like in their head, but things become very easier if you make the choice diagram. I do it too, and it makes things a lot easier. Like now, you just list out the options that you have at n comma v. There are only two options. Now we have a smaller problem, and then now we have the solution. Once you have a smaller problem and we have the base case sorted out, we have the solution. Got it? So basically, this is the bigger problem. This is smaller problem 1, smaller problem 2, and then now we again do this further till we reach the base cases, and then we tell what the base case looks like. Now, if elements could be taken infinite times, there is a slight modification here. If elements could be taken infinite times, it's Wn plus Lw of n comma v minus Vn again, n comma v minus Vn. Yes, only in the first one you either pick the nth item some one time, and again you have the same problem again. So Akshay is asking if you could pick the nth item infinite number of times, any item infinite number of times. That means you either pick the nth item once. If you pick the nth item once, you're calling the same answer again. N minus 1. You don't write n minus 1 here, but here you write n minus 1 because you choose to never pick the nth item, or you pick the nth. This is picking the nth item at least once. Now we have the same problem again. Hope that's clear. If you write down the DP state, if you write it down the state table, it'll be more clear to you. I'd suggest you to write it down. All right. N instead of n minus 1. Yes, exactly. You're absolutely right. Yes. Awesome. Now let's get to coding the solution. Is this clear? Do you want to re-explain any part of it? People in the live chat, you need to subscribe to actually talk to me in the live chat. So yeah. Any doubts? Are you okay if I go and code the solution? Actually, why are you deleting a message? It's perfectly valid. Awesome. Awesome. I'll go ahead and code the solution. So what do we have here? This is basically a new variation of Knapsack, and I'm coding the solution right now. So before coding the solution, let's first brief out the solution before coding it. What do I need to do here? First, I need to compute LW of n comma v for all n comma v, right? For all n comma v. Now, what do you mean by for all n comma v? N is up to 1 less than equal to n less than equal to n, this n. V is basically 0 less than or equal to v less than or equal to maximum value that you can get, which is basically there are 100 items and each item's value can go up to 10,000. This is basically 10 power 5. Right. It's as simple as that. So once we compute LW, we call that LW. We first solve the recursive approach. Solve n comma v. Now that in this problem, I'll directly use the storing the answers, because we already discussed how to convert the recursive to like memorization in the previous solution, previous video. I'll just directly use DP here. Now solve n comma v. All right, let's first do this then. Same problem. The input looks exactly same. So what do we have here? Or like I'll just code the recursive as well. Like what's there? LL max value equals 1e5. Now DP, I'll just write it const so that I can initialize an array with it, or like later. So what do we have here? LW, the function that we talked about, int n, int total. Now let's write the base case here, straightforward. If n equals 0, n equals minus 1 here, meaning I'm using 0 indexing, so because it's convenient now, return 0. Now if total value equals 0, if total value equals 0, what do we have here? We have a small condition here, if n equals minus 1, Let's define int as LL infinity is equal to 1e 15, 10 power 15. Okay. Now you have no items left if n equals -1. If total value is greater than 0, return infinite, because now you have no elements, but you have some value left. You want to tell the upper state that, hey, this is not possible. How do I tell that? By telling that my value is infinity, because I'm taking the minimum weight, right, at every time. If total value equals 0, return 0, because I can get 0 value with 0 weight directly. So why not do it? Some might say this is not required, so that's up to you. Now let's take. If we take equals LW of n minus 1 total value minus values of n plus weights of n. Exactly what we wrote here. Exactly what we wrote previously. Isn't it? Awesome. Now, but what if values of n is less than, like it's greater than total value? What if it's greater than total value? So that's why we initialize this with infinity. If total values of n, I'll tell you, I'll explain everything. Total value. Then do this. LL don't take. It's just LW of n minus 1 comma total value. It's as good as you're not caring about n. Now return minimum. This is lowest value, so you need to take minimum. Minimum of take comma don't take. Got it? And now let's initialize our answer as answer equals 0 for int v equals 0, v less than equal to max val v plus plus if lowest weight of n minus 1 comma v less than or equal to w. Like this is saying, if we can achieve v with under w, answer equals max of answer equals v, because we are incrementing going from, or we can just write answer equals max of, it's the same thing, but I'm just writing it so that, yeah, to explain less here. All right, awesome. Now here, what are we doing here? If values of n is less than or equal to total values, you take it. There's an option to take it. With basically n minus 1 and total values minus values of n, right? The other option is weights of n. Got it? The other option is we don't take it at all, n minus 1 comma total value. Now we return minimum of we either take or we don't take. Got it? We either take or we don't take. Is this clear so far? Is this clear? I initialize it to infinity because if we can't take that value, then minimum of infinity comma don't take is basically don't take, right? Don't take. We should not consider take if we cannot take, right? If we can never take it, we shouldn't consider take. That's why, and this will give you minimum of infinity comma don't take is basically don't take, because infinity will be too high. This can also be too high, but that's irrelevant to us. Is this clear so far? This is clear. Any doubts so far? I'm looking at the live chat. Any doubts so far? Would you like me to, the complexity of this, I want you to tell me what do you think is the complexity of this? Awesome. Awesome. All right. What is the complexity of this? So at each n, we are either taking Prajwal, nope, it's not O of n yet. It's not O of n yet. It's not O of n, nope. At each stage, you're either taking or you're not taking. And you're not memorizing at all. You're not memorizing at all. If you're not memorizing at all, then like at each step, at each stage, you're going to Maxwell times. It's Maxwell, it's exponential basically. At each stage, for each n, you're doing 2 operations, right? Yeah. But we are calling this for each n, right? We are calling this for each n. And the complexity for calculating LW, this function, is O of 2 power n, right? Because solve of 2 cases. It's again 2 cases. Like biggest one 2 cases. And again this one 2 cases. Again this is 2 cases. We're computing it each and every time. 2 power n. Aniket got it right. Yes. It's 2 power n. O of 2 power n. Or you can write O of 2 power n into v. But all we need to know is that it's exponential. Got it? Is this clear? Yeah, we're taking 2 decisions for every n, which is essentially 2 power n. Awesome. Now, how do we reduce this? 2 power, what's the, let's look at the 2 power n is basically 2 power 100, which is very huge. It's way higher than 10 power 8. Now, what we do here instead is, we basically store the answers. We store the answers. How do we store the answers? We've done it before. So, we store it as dp, LLDP. What is the state here, n and value? So, how much can n be up to 101? 100. And total value can be up to maximum value, 10 power 5, max value. Right. Now, for int I equals 0, I initialize dp. I need to initialize the dp, right? For int I equals 0, I less than equal to 100, I plus plus. For int j equals 0, j less than equal to max val, j plus plus, dp of ij equals -1. By telling that it's -1, I'm telling that, okay, all the states are not visited. None of the states have been visited yet. I'll visit them one by one. Got it? All right. Now here I write dp of n total equals min of take comma don't take. Now return dp of n total. This is still exponential until I add the lazy step. If dp of n total, if this has not been visited, then return it already. Why do you need to compute it again if you have already computed it before? This is your this is saying got this? This is the memorization part. All right. Awesome. Awesome. Is this clear so far? This is clear. This might give you a TLE again because, function calls and so on. 10 past 7 function calls. Is this clear so far? What did I do here? The lowest weight I can achieve with n items and total value to this total value. If there are like no items left, if total value is greater than 0, return infinity. Otherwise, just return 0, because if total value is greater than 0, that case is never going to happen. You can't achieve it, like with no items and you need to achieve a value. That's not possible, right? Awesome. If total value is 0, you just return 0. This is probably not necessary, but yeah. And this is if you've already computed the DP. If you've already computed the state, don't compute it again. Now, we either take the nth value or we don't take the nth value. If we take the nth value, there are n-1 items left. Now, what do we have here? Total values minus values of n is our new values. New value, we are calling the smaller problem. This is how it will look. And now, since we've taken the nth item, we need to add the weight to, like if we take it, right? Take the nth weight and then minimum of n-1 weights, n-1 elements, items, and this is the target total value. If we don't take, it's as good as n wasn't there at all. Basically n-1 in total value. And this is basically taking the minimum of both the weights. Is this clear? Any doubts with the solution? Any doubts? Do you want me to re-explain any part of this? Got it? Awesome, awesome. Awesome. All right. Yuvraj asking, so do we have to write any return statement after line 27? 27? Nope. You don't need to write anything after line 27 because we need to consider both choices, taking and don't taking before actually deciding anything. That's why you should like first look at this code and digest it first. What each line is doing. This is computing if it's already returning. This is returning if it's already computed. Sorry about that. And this is choice 1, choice 2. Best of both choices and returning it upwards. And all this is like just base cases, boring base cases, but still you have to write it. So let's write it. And then in the end, we're writing over all possible values and we're seeing which of these values are going to be less than, which of these values can be constructed so that it's less than W. The best weight is less than W. And we take the best of all those values and put it in our answer and we print the answer simply. Straightforward, right? Any doubts so far? Any doubts? Awesome, awesome. Now, this is the recursive approach which is going to give you a TLE. How do we do the iterative approach? How do we do the iterative approach? Let's do that. We do the same approach again. All right, very similar approach. Let's erase everything. Very similar approach. We just make it iterative. Now, we don't need this. Like, we're not visiting iterative approaches. Don't need like so much initialization and all. For int total equals first int n equals 0. Items, okay, items equals 0. Items, we're using one indexing here because items is the number of items here and it's easier to compute. And items plus plus for int value, total value 0, total value less than or equal to max val, tot val, plus plus. Now, what are the base cases there? If basically items equal 0, dp of, yes, it's always good to think in terms of state while solving these kind of DP questions. Yes, dp of items comma total value. If items equal 0, there were two cases. If total value is greater than 0, else two cases. That means that you have no items, but you need to make a total value. How will you make it without no items? So that's why we write it as infinity. dp of items total value equals inf. If, and the other cases, total values is equal to 0. That means dp of items equals 0. Straightforward, right? All right. Else. Now, what is the other case? The other case is essentially, the choice where you take or you don't take. You take, I'll take. First, we initialize it to infinity. If we can take, that is, if values items minus 1. Note that I'm using one indexing here. The items is the count of items. So if items equals 1, it means the first item, which is basically values of items minus 1, is less than or equal to total value. Then take equals dp of items minus 1, because one item less, and total value is also reduced because you took this item, values of items minus 1. Now, since you've taken this, your weight has been increased by weights of items minus 1. LL don't take is simply you don't take it. It's as good as n isn't present. Basically dp of items minus 1 total value. Very simple. Now dp of items total value is simply equal to the best of both. You take or don't take, which is basically minimum of take comma don't take. Right, that's it, right? And now what do? We iterate over all possible values. Int val, int answer, we write int answer equals 0 initially. Int let's say v equals 0, v less than or equal to total val, v plus plus. If dp of n v is less than or equal to w, answer equals v, or you can add max of answer. So we are iterating over all possible values, and we are seeing if it's less than or equal to w or not. If it is less than or equal to w, that will be our answer. Like we are updating our answer, and we take maximum of all answers. Right? Is this clear? Is this clear so far? Any doubts? Any doubts here so far? Awesome. What do we do here? If items is 0, total value is greater than 0, then you can't make, when you have no items, you can't make any, you can't make an item with total value or something. Like that's why we label it as like you cannot take. That's why we are marking it as infinity. Now, if we can take, if the other case is when the total value is 0, and the other, if else is like if it goes inside else, it means that items is at least 1. Like so now if you either take or you don't take. Now if you take, Good to hear that, Nitish. So if you either take, then you have one less item, and now your total values is reduced, right? It's been reduced by values. Since you've taken this item, values of items minus 1. Like, you're taking out this item now and putting it in your bag no matter what. So this weight is definitely added, plus whatever the answer is like underneath it would answer the smaller problem. If you don't take, it's as good as the item didn't exist. You move on. Now you take minimum of both take and don't take, and that you put it in your answer. And this part is basically you're iterating over all values. This part you're iterating over all values, and now you're taking the best of them. Like, if you can achieve a value with under the budget, then take it up. Like, take it up, because and you've taken the answer, the maximum of all such answers. You're printing the answer. All right. Is there any part you'd like me to re-explain? Is there any part you'd like me to re-explain? I'll be happy to re-explain this part. All right. If it's clear, do let me know in the live chat that it's clear. Awesome, Nitish. Thanks. Aniket, Yuvraj, and the other people, Akshay. People in the live chat, please let me know if you want me to re-explain any part. And if it's clear, do let me know it's clear, so that I want to just add a few things to this, and then we can wrap it up. Is this clear? Got it? Awesome. 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 All right. Now what? Now you can expect what I'm going to do, right? All right. Let's see what's going to happen here. Let's discuss the time complexity. Time complexity is essentially, what are we doing here? First loop, second loop. All of this is just O of 1, right? We're not like running any loops or doing anything complex here. O of 1, 2 loops, that's it. And here it's just 1 loop. So, oh, sorry, I made a mistake here, Maxwell. There might be a few mistakes here and there in the code, but this is the basic idea. And this is what I did to solve the problem as well. Well, I made another optimization, which I'm going to tell now. So time complexity for this is essentially, what is this? N into Maxwell. And Maxwell is basically, so basically N is up to 100 and Maxwell is up to 10 power 5. And it's 10 power 7, which is acceptable under the time limits. Is this clear? Time complexity is that. What is the memory complexity? What is the memory complexity? It's the same, because we made a 2D array of 100 cross 10 power 5. 100 cross 10 power 5. It's basically N into Maxwell. Can we improve this further? I want you guys to tell me. If you've seen the last video, you should be able to do this. Can you improve the memory from O of N into Maxwell to something more better? Can someone tell me in the live chat? How can you do this? If you've seen the last video, you will be able to do this. If you haven't seen as well, like, you need to just make a tiny observation. You'll be able to do this. Make a tiny observation. What's the observation here? So look. Well, 1D DP, yeah, you can. As in, you probably can, but like the time complexity would be same, but you might might have to run 2 loops or something. But like nothing comes to my mind at the top. Like I think it would still need 2D DP. Like just that I'm not sure about this actually. Yes, Aniket got it again. Every time only item minus 1 is being used. Yes, that's correct. So we don't need to, yeah, exactly. Every time if you look at this, DP items, here you don't need anything previously. Here DP items is basically minimum of take and don't take. And take is using DP of items minus 1. Don't take is also using DP of items minus 1. Yes. So only DP items and DP items minus 1. You only need the previous DP. We need, for DP of items, we need only DP of items minus 1. We don't need anything before that. Why do we need it before? Like, are we using DP items minus 2 anywhere? No, right? Why do we need it then? Why do we need it then? We don't need it, right? So we'll do the same as what we did on the last problem. We chuck it off. We chuck this off and write LL DP of Maxwell. We need a big array. And then we current DP and current and previous. So I'm just going to do a tiny magic here. Everywhere where there's DP of items, there are 3 DP of items, then I replace that by current. Wherever there's DP of items minus 1, I replace that by previous. But there is one thing. I need to copy current into previous, right? Every time I'm finishing my current, I need to fill it into previous again, because current for items is going to be previous for items plus 1. So I'm going to fill previous as well. For int total equals 0, total less than equal to maximum val, like up till where I'm going. I'll just write less than actually, total plus plus. Oh wait, item shouldn't be here. Oh, my bad. One sec. My bad. Okay. One sec. Like, you don't need to mention which row because. Oh, wait, one sec. Yeah, this should do it. Now, previous of total equals current of total. All right. Now here, what comes here? Can someone tell me in the live chat what comes here? We can write current or previous. That's correct. We can write previous as well. We can write current as well. Both are gonna work. Got it? Are there any doubts in the solution so far? Any doubts? Is there anything you'd like me to clarify? Is there anything you'd like me to clarify? Is there anything you'd like me to clarify? Awesome. Now look what we're doing here. Sometimes you have to be efficient, and if someone asks you like, hey, how do I reduce the memory complexity of this? Now you go back and like, how would you have done it if you had done it on your own? Now you look like a DP of items. It's using only DP of items minus 1. I don't need anything previously. Like, you draw a table and you see what at some point you're using only the row before it, which means you won't be able to, like, using all of it would be useless, because at one point the previous rows won't be useful anymore. Like for DP of 5 values, you don't need DP of 3 values. You just need the row of DP 4. That's sufficient. So we just store current and previous. That's it, right? Kapish, I'm not able to understand your question. Can you frame it clear? I'm afraid I won't be able to cover it in this class because of the time constraint. All right, what's the time complexity here? time complexity for this question, for the new modified version. Again, we're using 2 loops. Nothing changed, right? It's basically O of n into max val, which is basically about 10 power 7 again. Time complexity hasn't changed, but space complexity changed. O of, what do you declare here? Just max val, right? O of max val. Is this clear so far? We reduce it from O of n into max val. So we reduce the space by n times, isn't it? We were more efficient in space by n times. So we know that time is costly, but like in real world, space is costly too, right? If you want to buy a hard disk, it's going to cost you something, right? So you're saving it by n times, for example, in this case. All right. Any doubts? Do you want me to re-explain some part here? Any doubts so far? All right. Yes, space code. Awesome. Yeah. Good job. Yeah. Also, if you haven't, yeah. Awesome. Also, I've postponed my next session about longest common subsequence to a later time because I couldn't cover it in this session. And in this week, I'll be I'll likely be doing Codeforces math upsolving. So if you find math problems in Codeforces hard or difficult, I'll be doing it there. So I'll be doing it in that class. So do attend that. Any doubts? Is this clear? Do you want me to re-explain this part again? Huh? Awesome. Awesome. All right. Oh, Yuvraj. Okay. Yeah, sure, I will. I don't look at it that often, so I'm sorry about that. So what did we do here? First, knapsack. This is the second variation of the knapsack where the values are small but weights are huge. If values are huge and weights are huge, it's an unsolved problem to solve it like very quickly enough, within time. If values were also 10 power 9, I don't think there's a quick algorithm to solve it under 1 second. Aniket, the next class it's gonna happen, okay, I'll ask them to put up the community post. So you can follow the community post and you can also subscribe to the Telegram channel. As I said, there are going to be live updates on the class on the channel about when the classes are going to happen. And okay, let's just revise what we did here so far. Again, what is the question? There were n items, and for each like there were n items, and each item was either had a weight and a value. Now you want to pick some items to maximize your value, but you can't pick all of them because there's a budget. If you pick all of them, you might exceed the budget. So you need to be within the weight budget and maximize your values, right? So what did we do? In the previous problem, we tried for n items, and if you have a budget B, what is the maximum value that you can achieve? We did that because we had the what do you say? We had the weights were small. Now the weight is like really huge and the values are small. So what did we do? We did the reverse. We found what is the lowest weight that we can achieve. Like, say we want to achieve the value V with n items, picking some of the n items. what is the lowest weight among all the choices that have the value v. Once we did that, we had the dynamic programming, we had the recursive approach. Like once we know what is the best weight that we can get for a value v, we iterate over all values v, and we find the maximum value whose weight is under the budget. Since we need to print the maximum value, that's what we do. Maximum value but weight under budget. That's what the question asks, right? Maximum value but the weight is under budget. Print that. First we did the recursive approach. Then we memoized it inside it, like so that once the recursive approach, at each end it's taking 2x time. So at each end you have two choices, and you go at the lower end. You keep doing that. That can be 2 power n, right? Alright, that can be 2 power n. Now once that's 2 power n, what did we do? We saw that the number of states were just n into max val. We saw the number of states for n to max val. So we used that observation and we found out that each state was being recomputed multiple times. Since it's being recomputed multiple times, we just store it and return it instead of recomputing it multiple times. So we compute it exactly once, and next time the same state comes up, we return the answer. This way we won't recompute it multiple times, and we are being lazy about it by storing the answer and returning it, like a cache kind of thing. It's not a cache, but yeah, that's what, like, you're storing it and returning it. And then we store it and return it, and then we found out the space complexity was O of n into W, because hey, you need to store the state somewhere, right? N and max val. And the time complexity was clearly O of n into W as well, because we reach sometimes you can reach all the states as well. Then what did we do afterwards? Then we converted that into iterative. Iterative was straightforward, I think, because it is same as recursive, but we put the conditions inside the 2 for loops. Again, we found the space complexity and time complexity was the same. Time complexity and space complexity was the same. What did we do after that? We found an observation that the DP of items for DP of n comma, like basically lowest weight of n comma value, depends only on the n-1 row, n-1th row. We don't need n-2 and d. Lowest weight of n comma W will never call lowest weight of n-2 comma something. It will only call lowest weight of n-1 comma something. So we can be lazy about storing our values. So we just store the previous state and the current state. And once we compute the current state, we store the previous state and the current state. And once we are done computing the current state, we put all the current state into the previous state. Why? Because the current state for I is going to be the previous state for I plus 1. That's why I was putting into previous. And once we're done with all that, we did the same thing, for which current is basically the best weight. If best weight for V is less than equal to W, then V can be our V is an achievable value. Now over all the achievable values, we take the maximum, and that's our answer. Got it? I hope this is clear. And if you found this class useful and if you found this class educational, please don't forget to like, so I know that you're actually enjoying it. If you found it a bit, like, if you have any comments or anything, please do let me know in the live chat if you want me to improve some part of my teaching, or please show it in the comments as well. I'd be happy to learn from any valid feedback. Awesome. Then I guess I'll see you in the next class. Now we're done for today. These are the two variations of Knapsack, and usually I think a lot of Knapsack problems, or Knapsack related problems, revolve around these two. So in the first problem, we took the max. Here we took the min because we wanted to maximize the value. This problem, it's basically the inverse. Basically the inverse, right? We are fixing the value and we need to minimize the weight. And over all weights, we iterated over all values. We checked which which value's best weight is under W, and all the achievable values basically. All the achievable values we take the maximum because the question asks for the maximum value, right? So we print that. Awesome. And that's it. So I guess we're done for today. And as I said, if you do subscribe to the Telegram channel for more updates on my classes in general and other classes as well. And if you haven't liked it, please do like it already if you think it's useful. If you think it's useful, please do like it. And if you think it's going to be useful for your friends, do share it with them as well. And there's going to be a lot more content like this coming up. So if you do want to if you want to keep learning, and if you want this content to show up on your YouTube, don't forget to subscribe. Thank you. Have a nice day. Have a nice education day, and yep. Yeah, thanks all for that. Thanks Nitish. Thanks Viraj. Hope you all understood it. Good luck learning DP. I'll be taking more classes on DP, and if I'll be explaining in a similar way for maths as well. If you haven't checked out my math course as well, do check it out. It's going to be useful. And I'm going to take another session, another playlist called Maths Code Forces. Code Forces problems, math problems have been a bit tough for some people lately, and people have asked me. So yeah, there's that. I'm going to take that too, probably in the next 2-3 days or so. Okay. See you guys.